So now what we understand is that all bacteria can talk to each other. They make chemical words, they recognize those words, and they turn on group behaviors that are only successful when all of the cells participate in unison. And so now we have a fancy name for this. We call it quorum sensing. They vote with these chemical votes, the vote gets counted, and then everybody responds to the vote. And what's important for today's talk is that we know that there are hundreds of behaviors that bacteria carry out in these collective fashions. But the one that's probably the most important to you is virulence. So it's not like a couple bacteria get in you and then they start secreting some toxins. You're enormous. That would have no effect on you. You're huge. But what they do, we now understand, is they get in you, they wait, they start growing, they count themselves with these little molecules, and they recognize when they have the right cell number that if all of the bacteria launch their virulence attack together, they're going to be successful at overcoming an enormous host. Hi, I'm delighted to be back to give you a little progress about what we've been doing in quorum sensing. And so today I want to tell you one story about how we're taking what we learned about these bacteria talking together and trying to interfere with that conversation to make a fundamentally new kind of antibiotic. And so the story I'll tell you about concerns this pathogen, Pseudomonas aeruginosa. This is the bacterium that kills people who have cystic fibrosis, it kills immune-compromised people, and it causes infections when you get a catheter, a stent, or a breathing tube. And the reason Pseudomonas is so virulent is because of this chemical communication, this quorum sensing. What Pseudomonas does is that as it grows, it makes and releases small molecules, which are the red triangles on this slide. And so as the cells grow, these molecules that are outside of the cells increase in proportion to cell number. And as you heard on the clip, when the bacteria detect that those molecules are there, they interpret that that means there's other cells around. And then as a collective, all of the bacteria together make a biofilm, which is how they sit on surfaces and adhere to tissue, and then the group together secretes the poisons, the toxins that make us sick. So that's quorum sensing. And so we want to be able to interfere with that conversation. And so we know what the molecule is that Pseudomonas talks with. It's the one that's on the left side of this slide. And so what we did using chemistry is we changed the structure of that molecule to make the one that's on the right. And so what that chemistry did was it changed the signal molecule, the word, into an inhibitor. So we changed the molecule that turns on quorum sensing into a molecule that shuts down quorum sensing. So what happens if you have such a molecule? So first I'll talk about biofilms. So in this Petri plate, what we've done is we've put Pseudomonas in the middle of the Petri plate. And what I hope you can see is that the bacteria have spread out to the edges. That's this biofilm formation. As a group, they move out over the plate. And that could be like your tissues. But we have this inhibitor. So now if we do the experiment, we put the Pseudomonas in the plate and we add the inhibitor, what you can see is that the Pseudomonas can't move. So that's good. That's step one in the infection. It seems like our inhibitor can shut down biofilm formation. The next question for us is, what about these poisons, these toxins that Pseudomonas secretes? So now you're looking at an experiment, and in the left-hand test tube, that's wild-type Pseudomonas. It's doing quorum sensing, and it's secreted these toxins. And when it secretes those toxins, the bacteria turn green. In the middle test tube, that's a mutant that we've made, where we've knocked out its quorum sensing system. So that mutant has no communication, and what you can see is that the bacteria are colorless. They can't secrete the toxin, so they don't turn green. The right-hand test tube shows you wild-type Pseudomonas that we've added our inhibitor. And what I hope you can see is that the inhibitor greatly decreases the ability of Pseudomonas to secrete that green poison. So now we're in business. It looks like, at least in the lab, we can shut down biofilms and we can shut down toxin secretion. So what about in an infection? So in this experiment, you're looking at an animal model system that we have for Pseudomonas infection in the lab. And all we do is measure whether the animals are alive or dead. And so on the line that you're looking at, obviously if we don't add Pseudomonas, the animals are perfectly fine. If we give a Pseudomonas infection, now what you can see is that all of the animals die within the first day after the infection starts. But if we do that, we give the Pseudomonas infection and we give that inhibitor molecule that I showed you, what you can see with the third line is that we can greatly improve the outcome for the animal. So in fact, we think now that there must be merit to this idea of interfering with chemical communication and that maybe this could form the foundation of a new type of therapeutic. And so what we're doing in the lab right now is we're taking the molecule that I showed you and we have to make it more medicine-like. We have to build in potency and we have to make that molecule safe. The second thing is that we got inspired by that biofilm experiment that I showed you, and we're working with engineers now to try to embed those inhibitor molecules into materials. And the idea is that maybe we could make infection-resistant catheters or stents or breathing tubes. And then finally, I'm just telling you one little vignette that's about Pseudomonas. We work on lots of globally important pathogens in my lab, and we're having similar success doing these kinds of strategies in other bacteria as well. And then to finish, I just want to show you the two students who did the work, Colleen O'Loughlin and Knut Drescher. They both work in the lab, and I'm lucky to get to work with them every day. Thanks for having me back.
That's so interesting.